Well, I've been in the Chesapeake area for 20 years, and I did a master's quite some time ago at Horn Point Lab. So I learned a lot about estuarine ecology and water quality. And so then I went off to
Hmm.
California and did some work in the Sierras, and then went to Brazil and did some work in the Amazon and in the southeastern portion of Brazil, and then went up to Woods Hole for a couple of years and Cornell, and then ended up here. So a lot of bopping around, a lot of different ecosystems, but Chesapeake Bay is been very interesting for me. So the first decade, I kind of focused on Chesapeake Bay water quality issues and developing metrics for ecological health. Did some pretty nice publications on the Chesapeake Bay, and more recently, I've turned my focus to depressional wetlands on the eastern shore, looking at carbon dynamics and greenhouse gas fluxes. And then a part of my research portfolio is also looking at stream restoration performance, which I've been doing pretty actively over the last decade for a number of different sites. And so my talk tonight will be on one form of stream restoration, a design called a step pool streamwater conveyance. So I'm going to talk about a study that's been done on one of these stream restorations that's been implemented on the University of Maryland campus in College Park, which has made it very easy for us to do the sampling and get student involvement. And so the sampling has been, very robust and consistent over the 7-year period that we've received funding from the Department of Natural Resources to do this. So, as opposed to other sites where you have to get in a truck and drive a long way and crawl down a ravine to get a water sample, we can just pop over to the stream and get a base flow sample or set up an auto sampler to collect a stormwater event, and it's made it very easy to get really good, high quality data. So I consider this to be kind of you know, a very nice study, and it's one that I'm comparing with 3 other study sites that are of a similar design in this manuscript that's going to come out in ecological engineering. And I consider this to be kind of the final word in terms of the capabilities of these types of nutrient or these types of stream water restorations, the step pool conveyances, to actually reduce certain nutrients, namely nitrogen and sediments, pretty consistently. So with that, okay, so we'll go to slide 2. This is an aerial photograph of the section of Campus Creek that's being restored. The individual sectors are color coded. And for the purposes of the talk and the manuscript for ecological engineering, I'm going to be focusing on what we call phase 1, which was basically the upstream portion of these segments. So if you look at the yellow and the purple, and about right down to here in the red segment, just above XS6, this is the portion of the stream that's been turned into a step pool conveyance. You can see some images of the stream before it was restored, varying sized. A lot of refuse. You can see the bottom left, a lot of refuse in the stream. So it was a very good candidate for some upgrading and restoration. And I should mention that this study's been ongoing since 2017. So it's been a nice 7-year period, which is also pretty uncharacteristic for these types of studies on stream restoration. Typically, you get, a year if you're lucky pre-restoration, and then a year or two afterwards to do the analysis of potential reductions of these pollutants. And so this has been very nice to follow this along a longer time period. And also because we're going to have this lower portion of the stream rebuilt over the course of the next few years. The first third of that phase 2 has been done already last summer. We have another sector, which is the next sector down towards Paint Branch River, which is going to be done this next summer, and then potentially the final segment the year after. But the current image shows the land use map for the entire catchment and our monitoring station positions along the stream reach. This is a little bit unusual in terms of the land use configuration for an urban catchment, in that we have the University of Maryland golf course and the headwater. So it's a very pervious headwater catchment with a lot of grass and forest. and the impervious surface for the watershed, the sub-watershed or sub-catchment of the watershed is only 19%. This is pretty low for an urban catchment, particularly by comparison with some of the other highly impervious surface areas that are in some of the other comparison watersheds in the study. So it's 163 hectares. This is from point B, which is the post-restoration monitoring station. And point A is the pre-restoration monitoring station shown here. You can see that this sector of the stream is also heavily eroded. There's a wall here that's kind of holding a stormwater BMP intact, but it's pretty much failed. And you can see in the aftermath of the restoration how that's been graded back, and the stormwater BMP has been retrofitted. It's a lot of granite to try and stabilize that channel. And then there are the series of step pools that are upstream of that. These are the same pictures, a little bit larger, just showing the pre-restoration period from October 2017 through June 2019, and the post-restoration below it, October 2019 through the end of last year. Again, the study is ongoing, but we're focusing more on the downstream portion of the stream for phase 2. The photo on the right is just a downstream view of our sampling station. It's got an auto sampler in there, and this is again the one that's positioned at that position number B, which is just downstream of the upstream portion. So for those of you who aren't familiar, the step pool streamwater conveyances, or SPSCs, are intended to decrease nutrient and sediment loads, create and improve aquatic habitat, and recharge groundwater. It's supposed to provide more interaction of hyporheic water with the stream, which doesn't happen as much with heavily incised stream banks and stream water. So basically, if you have a very incised urban stream, you fill it up with soil and top it off with topsoil, but then you also build these little ponding basins using boulders and silica cobble, and you can fill the sand matrix, the infiltration matrix, with sand and soil, and then RSCs, which are a type of streamwater conveyance or step pool streamwater conveyance. They actually include quite a bit of organic matter in the form of wood chips and leaves. That's meant to try and kickstart some of the biogeochemical processing that you get in natural stream environments by providing an energy substrate for microbes. So theoretically, this enhances some biogeochemical processes such as denitrification. This particular step pool conveyance on the University of Maryland campus does not have a lot of organic matter embedded into it, so it's really more of a traditional step pool conveyance. So I make that distinction in the manuscript pretty clearly, so there's no confusion. So anyway, you can tell by the schematic what the idea is here, that you have these step pools, the stream water comes into the step pools and is retained, so this basically decreases the velocity of the runoff, and so you don't get as much erosion. And then the water that's retained inside of these little step pools, it has time to both not only provide settling of sediments, but more interaction with the floodplain and hyporheic zones, so you get more biogeochemical interactions, and then infiltration of some of that water into the groundwater. Another aerial photograph with a schematic superimposed on it, which shows the actual step pools that were developed for this particular restoration. There are 15 pools from the top, which is right next to University Boulevard, and downstream to pool number 15. You'll notice also that there's some large retention ponds, stormwater retention ponds. The one I spoke about that was over that ridge in the photograph. This is the big one that's below the parking garage. And then there's another one where the runoff from this parking lot feeds into it. And that's also been retrofitted. And there's some smaller step pool conveyances that are implemented at various locations along the stream reach. So, and then some photos that show, of course, what we're seeing at various locations along the restoration. Should mention also that the green area is a forest conservation area. And one thing that we find is that tree removal is something that's very undesirable on the part of people when they look at stream restoration. And all of these stream restorations of steppable conveyances that I'm comparing in this manuscript have very few trees removed. So tried to leave as many trees intact as they could. And because of the forest conservation here area on the University of Maryland campus, they were particularly careful not to remove a lot of trees. So the objectives of the work were really to look at continuous monitoring of precipitation, deposition, and then of course the stream runoff and chemistry. We're looking at the pollutants of interest would be nitrogen and various fractions of the nitrogen, so nitrate, ammonium, total and total dissolved nitrogen, and also then phosphorus in those fractions, and then total suspended solids, which is different than total suspended sediments, because that includes more than just sediment. It's any particulate matter that comes out on a glass fiber filter that's greater than 0.7 microns. And so in order to do our research, we're looking at base flow and storm flow. We tease those apart. Base flow is, of course, the water that's in the stream in between storm events. And you have to give the hydrograph time to come back down to kind of a previous base flow regime. And before you consider that to be base flow, that's usually 1 or 2 days after a storm flow event. But we're collecting anywhere from 2 to 4 base flow samples per month. And so over the course of the 7-year study, we've collected 44 pre-restoration base flow samples and 124 post-restoration, which is quite a bit for any study in storm flow. We're collecting on a monthly basis throughout the year, and then we've collected 190, these are samples, 190 pre-restoration samples, 731 post-restoration samples, and that translates into about 21 storms in the pre-restoration period, and then 49 events in the post-restoration. So there are about 10 samples per storm event, which we're analyzing not only for volume-weighted discharge, but also then the chemicals in those particular time intervals. And that gives us a very accurate estimate of the flux over that storm interval. So again, these data then are used to determine the nutrient sediment concentrations and loads, and then we can compare the pre and post restoration differences. Hopefully we see reductions in the post restoration period. We're also looking at dissolved oxygen and specific conductance using probes which are collecting data at a pretty high frequency, so at 5-minute intervals, so we get all the transitions on a diurnal basis, and also over the storm flow hydrographs, which provides us with some important information. As I mentioned, precipitation is a large component of this. We have a tipping bucket rain gauge, which is located just to the north of the border of the watershed in an enclosed area, and we maintain that. There are also a number of other precipitation gauges that have been implemented more recently through the University of Maryland, a micronet system, and that's come in handy because there have been periods where we've had malfunctions with the rain gauge more recently. You know, like a darn spider making a web in there, and the tipping bucket didn't change, and it didn't tip. And so I've been able to fill in the gaps. And so the data are very robust, very complete. And you can see here in the upper right-hand panel, this is the cumulative daily precipitation in millimeters, which shows for every year of the study how precipitation accumulated over the course of the year. And you can see, just pointing this out, that the blue lines 2018 and 2020 are much higher than average. Typically, we get an average precipitation in this area of about 1,100, 1,200 millimeters per year. And then we've got 2 kind of average years and then 3 below average years with the black and the pink. So I highlighted the monthly precipitation values in millimeters just to show you how that changes on a monthly basis. Typically, it's a kind of a monomodal. You get higher storm volumes typically in the summer. But, you know, precipitation is relatively evenly distributed throughout the year in these catchments as opposed to many other parts of the world. But the reason that I highlight the 2018 and 2020 years is because I'm going to use those as the pre and post restoration comparisons for a lot of my talk and for the comparisons that I make in the study. So I do both with all the pre-restoration data and all the post-restoration data. But the reason that I chose 2018 and 2020 is because the water years are so similar. So when you're looking at fluxes or loads, you don't want to take a water year that's really high in the pre-restoration period and then compare that to a water year that's relatively low by comparison in the post-restoration period, because then your fluxes are obviously going to be lower, and you can't attribute that to the restoration design, because we really want to look at how the restoration is performing on an equal basis. And so having equal water years with the same amount of precipitation, relatively speaking, was a very nice comparison. And I was worried in the beginning because I thought, boy, if we don't get another big year, this study is going to be a little bit funky. But thankfully, we had another big year in 2020. So those, again, are the comparisons that I'm making, as in these box plots, which show the pre and post restoration nutrient and sediment concentrations for these 2 years. Again, 2018 pre-restoration, 2020 post-restoration, similar annual cumulative precipitation. And here we have storm flow on the top for Campus Creek. The bottom 3 panels are base flow. And I just want to point out that the box plots, for those of you who may not know what a box plot actually signifies or have forgotten, basically the bottom of the box is the 25th percentile and the top is a 75th percentile. So all 50% of the samples are within this box. And then you have a mean and a median line. The median line would be, for instance, the top line here, and the dashed line would be the median. And so, and then these are the upper quartiles with some outliers, which would be the dots at the top. So the comparison here is just a look at, I like to look at median concentrations more than mean. I think they're more representative in this kind of work. You can see with regard to nitrogen for base flow and storm flow, the medians decrease substantially. These are significant differences. For phosphorus, for storm flow, there's a significant decrease, not so much for base flow. And then you can see also for TSS, which you might imagine you'd see a big difference because of the retention capacity and the lower velocities with the stream restoration, that the TSS would be significantly lower. And that's what we see by comparison to the base flow, where you don't get a lot of suspended material. So it's pretty much the same for the pre and the post. So the data make good sense, but the bottom line is that we're seeing really good, nice reductions in nitrogen, some really nice reduction in storm flow, TSS, and phosphorus. Runoff comparison is something that I like to look at, particularly on a structure like this, where you've had a lot of lateral BMP effects with the stormwater retrofits. And this was kind of nice to tease out. This includes all of the pre-restoration data on the panel on the left here, and then a similar amount of time in the post-restoration period. But what I have here is a storm flow runoff coefficient, which is basically the percentage of rainfall which leaves our monitoring station in the form of streamwater discharge as a percentage, given the different storm sizes. So on the pre-restoration side, you can see that the relationship is fairly weak. It's 0.34 R squared, but it's kind of a scatter plot of runoff coefficients. And when you look at the post-restoration comparison, you can see that it's a much tighter relationship. And in particular of interest would be the lower size storm volumes, which show a much lower runoff coefficient, which signifies that the actual restoration is retaining a lot more of these water from these smaller size storms. And of course, the lateral BMP, stormwater BMPs, are a part of that retention. So to compare the loads then for this 2018-2020 water year comparison, again, I show runoff and then the nutrients and sediments of interest here. Runoff, again, as we might imagine from the runoff coefficients, is lower. It's about 13% lower from the pre to the post restoration period. Again, it was a result of the step pool conveyance retention as well as the BMPs. And then TN, total nitrogen, total phosphorus, and total suspended solids decreased by 32, 38, and 59% respectively, which are pretty good reductions for this kind of a stream restoration. Dissolved oxygen, again, we were using probes that are in not only the stream but in-stream ponds at the outflow where we have our monitoring station, and this provides us with high frequency dissolved oxygen data. This shows the dissolved oxygen concentrations in milligrams per liter, with the red line indicating the 5 milligram per liter, the criteria threshold, ecologically relevant threshold for 2019 and 2020. I just did a snapshot of this. We have the dissolved oxygen data for the entire study, but I just threw some rainfall on here to show you how the DO concentrations actually fluctuate, not only seasonally because of temperature and discharge, but then also with regard to changes during a storm event where you would have more of an oxygenation effect with the rainfall causing more turbulence and injecting dissolved oxygen into the stream water. But again, you can see that during the colder winter months where base flow would be higher, typically you have adequate dissolved oxygen. And then during the months of the summer, June, July, August, and even into the fall, when you have low discharge and higher water temperatures, you get higher biological oxygen demand, and then you get into a stage of hypoxia and anoxia, which is stressful for biota and can even be lethal. So we like to see the values above this 5 milligram per liter threshold, but you'd have to keep in mind that also there's some spatial heterogeneity within the restoration reach, and this fluctuates quite a bit in terms of oxygen levels. And there are always pockets of more oxygenated air, so fish can always survive for the most part, unless they're very extreme situations where there's very little flow over a prolonged period of time. So it's not necessarily a lethal thing to be underneath the criteria threshold, but it is taxing on a lot of this aquatic biota, particularly macroinvertebrates and fish. Specific conductance is another parameter that is interesting, just because there are criteria thresholds for this that have been developed by DNR for fresh waters of Maryland, and I forgot to look at exactly what those numbers are. I have it on my manuscript, but I think it's around 150 microsiemens per centimeter, and anything above that is taxing. It's difficult for aquatic microinvertebrates in particular to tolerate. And the average here is usually around 300 to 400 microsiemens per centimeter. But you can see that there's some dramatic increases with road salting in the winter months, where concentrations can go up as far as 2 millimolar, 2 millisiemens rather per centimeter. So that's 4 times higher than what this graph shows. And of course, then that it dilutes and bleeds out over the early spring, and into the summertime, you get kind of back to a stable condition. I mean, there's a lot of variability, again, when you look at the rainfall, where you get a dilution effect as a result of a rainfall event and then a concentrating period in between these rainfall events. And that's why I included the rainfall in there to show you why that it's so jerky. But again, this is not a real conducive environment for macroinvertebrates and the promotion of ecological uplift, which is one of the big concerns with a lot of stream restoration. We're trying to not only achieve these nutrient reductions, but to try and enhance ecological uplift, and all these places where we're doing these kinds of installations, whether it be the step pool conveyances or wetland complexes or natural channel designs, whatever, what have you. So with regard to the manuscript, that's kind of in a nutshell, what we have for the Campus Creek study, the important aspects of that. But then I make a comparison with 3 other sites. Again, the Linian RSE in Rock Creek is the study that was the Bossie study that was published in the Journal of Hydrology, which you have a reprint of. And that was a nice study that came out 2 years ago with Solange as a co-author. And then there are 2 other sites that are on the western shore of the Chesapeake Bay: Dividing Creek, which feeds into the Magathie River, and Saltworks, which feeds into the Severn River. And these are all, these 3 are RSCs, so they're the regenerative streamwater conveyance, which they have, anywhere from, let's say, 15 to 20% organic matter included into the sand and soil infiltration matrix. Again, that's different than the Campus Creek study, which does not have that, but the designs are similar. So I call them all step pool conveyances as a generic term. So for the study, then I look at the same kinds of box plots for all 4 sites. And on the right-hand side, you'd have for total nitrogen for each site, campus dividing, Linian, and saltworks, storm flow on the top, base flow on the bottom. And you can see nitrate is very responsive to these kinds of restorations. So typically we see significant decreases in total nitrogen. A lot of that is driven by the nitrate signal, because we do see enhanced denitrification. And so you can see again, the line here is representative of the median value. You have a significant decrease at every site with regard to the median and storm flow and in base flow. With regard to the storm flow in TSS, we see similar decreases. They're all significant. So that's very responsive, again, as you might imagine, for storm flow because of the increase in velocity and the suspension of sediment and other particulate matter, detritus and so forth, and periphyton that gets into the filter. So this makes good sense, but they are significant decreases for stormwater or storm flow. And then base flow, again, there's not a lot happening with regard to suspended material in base flow when you have quiescent material periods, or there's not a lot of velocity. So it's reasonable to assume that they would be very similar, which you see in Linian and Campus. By contrast, what you see with dividing and saltworks is an increase in the median value quite abruptly in dividing. And of course, you have to pay attention to the scale here. For saltworks, it's actually a different scale, so it's a similar or even larger increase. But that's a result of the iron oxidizing bacterial flocculate that you tend to see grow in some of these restorations. It's a natural phenomenon that occurs in a lot of the streams in the coastal plain in particular. But these restoration designs, they create habitat that is conducive to the growth and proliferation of this kind of iron oxidizing bacterial flocculate because of the low flow environments. And typically you get more interaction with the upper soil horizons. Sometimes you use bog iron, which is very subject to biogeochemical weathering, some varieties of the bog iron. So when it's more kind of a sandstone bog iron, that does biogeochemically weather and reduced iron gets into the stream, which the iron oxidizing bacteria utilize as an energy source, and they create this flocculate. So saltworks is one particular restoration that's got some of the largest densities of iron oxidizing bacterial flocculate that I've seen in any restoration. And so that's again responsible for this increase because some of that sloughs off even during low flow periods and gets into the filters. And so we see the increase, not a result of sediment, but as a result of this iron oxidizing bacterial flocculate export. I wrote a paper about that, by the way. If you want to see it, I can send through that reference. So again, one of the advantages of this longer term study, again, we're looking at 5.5 years of post-restoration data compared to 1.5 years of pre-restoration data, is to tease these apart by individual years, just to see whether or not there's some resiliency and constancy with regard to how these function. And I'll just point out a couple of interesting things that I get into more detail in the manuscript. But one thing that we get into in the manuscript, or I get into in detail, are some climatic anomalies. Again, we're talking about climate change, but there's some really crazy things that are happening. We've seen this happen with regard to very intense rainfall events, such as in Ellicott City. Turns out that we had one of those events with that kind of downpour in the upper catchment earlier in the study, just like the first year after the restoration, and it dumped 6 inches of rain over 2 hours. And if you remember the picture of the sampling housing, it's about 1 meter off of the kind of base flow level of the stream on the floodplain, and then the housing is about another meter high, and the water level came halfway up the water sampling fiberglass housing. And that's an enormous volume of water that came through the watershed. And as a result of that, the culvert that goes under University Boulevard to the very upstream portion of the restoration was like a fire hydrant, just blasting water into the sidewall of the stream restoration, and carved out this big hole and sent all the sediment into the upper two ponding basins, which reduced the water retention capacity of the restoration. So that was definitely an undesirable situation, but they rebuilt the sidewall, but the sediment remained in the upper tube, so that compromised the water retention capacity of the restoration, which is, of course, an undesirable. But I would suggest probably a commonplace thing that will happen more frequently with climate change and these kinds of events. So maintenance is also one important part of these stream restorations. You have to go in every once in a while and try and check and see how they're doing, and if possible, try and reconstruct areas that have been damaged due to climatic anomalies. Another one was a blowdown event. We had what's called uh, a long track bow echo event in 2022, and what we saw was a downdraft of over 145 kilometers per hour in the catchment, caused incredible damage all across the University of Maryland campus, but 300 trees were felled in the golf course area, and about 40 mature tulip poplars and red oaks and white oaks were felled and fell across the stream restoration um, main stem as a result of this storm. So there was an incredible amount of disturbance, a lot of uprooting of the root balls, and a lot of sediment, which was then laid bare. And just looking at the annual breakouts, again, if you take, for example, this is all for Campus Creek, and I did this for all the other sites too, but base flow in the pre and post comparison for the individual constituents that we're looking at, all data would be all the pre-restoration data compared to all the post-restoration data. And we're looking at median concentrations and what the median concentration in the pre-restoration period is compared to the post-restoration period. So when we have a decrease, that means that the median concentration is lower by, for example, in nitrate, in this example, by 44%. So if you look at TSS, and we follow this down, there's a lot of variability, but you start seeing a pickup in terms of the increased filtration and retention of TSS by the time you get to 2021. And then when you have this blowdown event, this actually shows that the concentrations were higher than the pre-restoration period, because it's positive here. This is for base flow. And then for storm flow, it went from -19, so it was retaining sediment, to exporting more sediment by a whopping 176% higher. Other things that happened would be with regard to ammonium. Typically, we see an ammonification effect after restoration, and so ammonium in the post-restoration period is typically higher, as you can see in the column here. These are growing season versus annual breakouts. But if you look at the annual for storm flow, it went from having more ammonium in the post-restoration period to actually utilizing more ammonium in the post-restoration period. So you have these really interesting transitions, and we're able to pick those up because of our sampling regime, which is pretty robust. 3 or 4 times we're monitoring for base flow every month and one storm flow event. So it's kind of interesting to see how these are picked up in our monitoring. That's why I think that the data are particularly robust for this study. With that, I'll just conclude. I got 3 more slides. Just by saying that as you might get the takeaway message, that these SPSCs are generally an effective means of reducing these pollutant loads. And what we see is pretty consistent reductions in total nitrogen and storm flow TSS. With base flow, it's a little bit more variable, particularly for TP and TSS. Again, that's in large part with the TSS due to the iron oxidizing bacterial flocculate that you get in the filters. Other topics that are covered in the manuscript that's currently been reviewed and soon to be published are the importance of certain design characteristics. We're able to make comparisons with the design characteristics of these 4 sites and then look at the water quality reductions that we see with certain designs characteristics, and it looks like water holding capacity is really instrumental in decreasing total suspended solid concentrations. So the idea here is that it maybe gives a little bit of play, a little bit of room for practitioners to potentially increase water holding capacity to try and retain more TSS if they have that ability with the design. Another problem with some of these is a constrained riparian or floodplain area that tends to reduce the effectiveness, nutrient reductions that we see with this kind of design. I talked about climatic anomalies, the 1 in 1,000-year precipitation event and the microburst. There was also an extended drought in 2024, if you'll remember the last year. It was pretty crazy. And that had an effect on water quality. One interesting thing that happened is that a beaver, after the microburst and all the trees fell down, one big tree fell right along one of the pool riffles. And a clever beaver just came up and said, "Boy, this is easy. I'm just going to use that tree and patch the little hole underneath the tree," and made a very effective beaver dam. And beaver dams have been studied before. I think the first evaluation of that in terms of water quality was done by Jordan and Carell at CERC way back in, I don't know, 1984. But they're pretty effective in terms of reducing nutrients and sediments, and so it's kind of an extension of the same idea that we get with the step pool conveyance. The step pools are kind of like miniature beaver dams. So the beaver dam was actually a good thing because it helps enhance the nutrient reductions. It was a bad thing because the water got diverted out of the side channel, and it circumvented a couple of the downstream step pools, but then re-emerged back into the stream downstream. But our estimates of the water holding capacity of the entire stream restoration is actually higher with the beaver dam than it was beforehand. And so as a consequence, the nutrient retention capacity of the stream restoration has been pretty much the same, despite that diversion of the water around certain step pools. So we talk about resilience and maintenance. Again, with all of the trees that fell down, those had to be pulled out of the stream, and then some replanting had to occur. So it's important to do that in order to maintain the integrity and the help maintain the nutrient reductions in the stream. And then I discussed some of the challenges of enhancing ecological uplift, which I had touched on before. And I'll just finish by mentioning that, again, this is the phase 1 reach that we talked about today for the purposes of the ecological engineering manuscript. We're currently, we're continuing this work not only by monitoring at the same position under phase 1, but also we have been monitoring phase 2, the outflow, with the same kind of a monitoring setup. And unfortunately, DNR has shifted its priorities, and we received money for the work, not only for phase 1, but phase 2 through last year. But they've suspended funding, and funding, of course, as you're probably well aware, is pretty difficult right now for environmental research. So to continue that, we're gonna look for additional funds. If any of you guys have ideas where we might be able to get some assistance in terms of that, we've got some really cool things that are on the boilerplate with not only continuing monitoring for the phase 1 outflow, but phase 2. Phase 2 includes looking at, again, the pollutant reductions with these different sub phases of phase 2, where they're taking segments of the phase 2 stretch and restoring them. I want to look at the detailed hydrology a little bit more than in this ecological engineering manuscript by looking at lateral inflows and their influence. One thing that's ongoing is looking at characterizations of turbidity in TSS. I'm working with Paul. Paul is with a friend, Nick, come up with a really nifty little, pretty inexpensive turbidity sensor. Most of these sensors, if you buy them through commercial companies, they're like whatever, $1,200, $1,500, and these are about a fifth of that cost. And this just shows an example of some of the stuff. I have an intern working on this with Paul, and very interesting data. We've collected about a year of data thus far. And this just shows an example of that for a storm event, where we have a sensor at the very top of the restoration reach, one at the mid reach, which is just below phase 1, and then one at the outflow below phase 2. And you can see that the timing of the peak of turbidity is staggered somewhat. The top comes out first, as you might imagine, followed by the mid-reach. But what's interesting is you can see a decrease in the turbidity from the top to the mid-reach, suggesting that there's a decrease in turbidity as the water moves through the restoration reach, which corroborates what we're getting with our total suspended solid measurements. But then by the time it gets to the outflow through the phase 2 reach, down to Paint Branch River, we have another increase in turbidity, which suggests that with the completion of the phase 2 restoration, that we'll probably see additional water quality benefits, similar to what we saw with the phase 1 reach. Lastly, end budgets for the entire Campus Creek catchment. I think that'll put what kind of reductions we see with nitrogen in a better context of what's actually being deposited, not only in the golf course in terms of fertilizer, but through precipitation and all the other inputs of nitrogen that you would tend to get. And then, of course, continued student involvement and training, which is really important. We've had about 6 interns over the last 7 years, and some of them have done honors theses on this. Turns out that the student that's currently working on turbidity with me and Paul, she's probably going to do an honors thesis in her senior year on this turbidity and some of the other stuff that's going on in the creek. So hopefully we can keep this project going for all of these reasons. And with that, I'll just again acknowledge the funding that came from the DNR, the Chesapeake and Coastal Services, which is now called Watershed and Climate Services, and leave you with a picture of the beaver dam. Don't have a picture of the beaver, never seen him, but he's there, as you can tell by this little stump that he chewed off about a year ago. And with that, I'll end. Any questions? Thank you.